Hello all. I'm Catherine Sanchna, a PhD scholar from IIT Madras. I'm one of the TAs of this course, Mechanical Characterization of Bituminous Materials. This tutorial session, I'll be conducting tutorial sessions every Tuesday between 6 p.m. and 8 p.m. And this tutorial session, the link for which is provided in the NPTEL website, and also this video will be recorded and posted in my YouTube channel, the link for which again will be given to you by the NPTEL website, NPTEL team. So if you have any queries, please feel free to ask in the discussion forum in the NPTEL website, or you can also comment below my YouTube video, the respective YouTube video. So without any further delay, let us proceed to the contents prepared by me for week 6 of this tutorial session. So I will share my screen now. Okay, so first let us see what this week's contents consist of. Okay, so first there were 2 lectures on DSR, which is the dynamic shear rheometer. Okay, the basics of dynamic shear rheometer given by Gala sir. Okay, 2 lectures on viscosity grading of bitumen and 1 on performance grading of bitumen. Okay, part 1. So we will be addressing questions in each of these lectures. Okay, questions taken from previous year's assignments. Okay, and as and when we solve each question, we will also be seeing some theory related to it. So we will address the questions in this manner. Okay, first we will address all the questions pertaining to dynamic shear rheometer, then we will go to viscosity grading of bitumen, and then we will proceed to questions which have performance grading related questions. Okay, so without any further delay, we will move to the first question. So this question is on dynamic shear rheometer. A largest surface area of interaction could be obtained from which among the following geometries? So before we understand the question itself, let us first talk some theory related to a dynamic shear rheometer. Okay. So dynamic shear rheometer is one of the equipments to characterize the behavior of bitumen. Okay. In addition to bitumen, it is also used to characterize the behavior of mastic, which is a mixture of bitumen plus filler particles. Okay, and these are particles less than 75 microns, of size less than 75 microns, or mortar, a bituminous mortar, okay, which will be bitumen plus fines plus filler. Okay, or it can also be a bituminous mixture. Okay, so it can also be a bituminous mixture which will have bitumen plus fine aggregates plus coarse aggregates plus filler. So these will be prepared in a larger scale, and later sliced or cored to the required dimensions. Why is it like that? Because in this scale, so in a dynamic shear rheometer, you have seen a dynamic shear rheometer, right? So it will have a maximum height with which it has a limited torque capacity, and also the height of the sample in the dynamic shear rheometer is also limited, right? Unlike you, so obviously you cannot use bigger samples. You can also always test samples in a smaller scale in a dynamic shear rheometer. So these two are samples which are prepared. Okay, the mixture is carried out in a larger scale, and it is sliced or cored to the required dimensions. Now if you see um, if you see any code for bitumen, so okay, there is no code for mastic. Okay, there is no ASTM code for mastic to be tested in a dynamic shear rheometer, but there are obviously codes for bitumen, okay, and also for mixtures. And in this case we will be seeing only tests on bitumen using a dynamic shear rheometer. Okay. So let us first understand this. Now if you see here, as the name says, okay, it is a rheometer. A dynamic shear rheometer is used to measure the rheological properties of a material. Okay. Now this rheological properties, okay, if I'm so it is the study of flow of materials. Rheology is the study of flow of materials, right? So when I say rheological properties and with respect to shear, okay, I can measure the properties in two ways. Either I can subject the sample to a rotational motion and measure properties. Mostly it will be viscosity. If I am subjecting it to a rotational motion, I will measure viscosity, okay, or I can subject it to oscillatory motion and I can measure properties like mod of the complex modulus, phase angle, storage modulus, loss modulus, complex viscosity, okay, and all that. Now if you see here, this is a time domain test. A few weeks back we have characterized testing on bitumen into two broad categories, which will be time domain tests and frequency domain tests. So if I measure time domain tests, if I do a time domain test, I can also, in addition to viscosity, okay, I can also measure properties like, I can also measure stress or strain, and from that I can also get the relaxation modulus or creep compliance. Okay, so this is the this is a very broad view of the tests in a dynamic shear rheometer. Okay, if you have to measure viscosity, okay, so let us take the rotational tests. For instance, if I have to measure viscosity, I will subject the material to different shear rates, okay, and measure viscosity. Now the thing is, here I will be also rotating the sample in one direction continuously. Okay, so uh, let us take, I've taken a sample in a cup in a quad geometry, and I will keep on rotating this spindle in one direction alone. If I have to do a time domain test, which I'm also calling it as rotational, because um, that say I'm testing a sample disk. Okay, so if I have to subject it subject the material to some kind of, say, loading and rest, okay, that is also a rotational test, that is also a time domain test. But here I will first say, this is the top view of my sample. Okay, this is the sample. So let us say this is, say, 2% strain, and 2% strain for this sample is this much. Okay, so I'll first rotate the sample in this direction to 2%. Okay, so this corresponds to 2% strain, and for a rest period, for if I have to provide a rest period for, say, 2 seconds, then I will go back again to the mean position. Here this is also a rotational test, but it will not keep, it is a time domain test, but I cannot exclusively call it as rotational, because it will not keep rotating, but it will like it will move in one direction, stay constant, and then move in the opposite direction. So both are time domain tests. In the case of a frequency domain, this is my mean position. If I have to apply a sinusoidal loading, my sample will first move in one direction. Okay, but the top plate will move in one direction, then again it will go back to the mean position. Let us say A, B, C. I've shown an animation of this also when we saw about small amplitude oscillatory shear. Okay, so this will be my B position, this will be my C position, and again it will move in the opposite direction. This will be my D position, and again E position. Okay, so this is my way of applying a frequency domain test, sinusoidal loading. Now why am I saying all this? In order to subject the material to these tests, I have to first choose the size of the sample. The size of the sample, and also the geometry which I'm using to apply this kind of loading to the sample. So how do we choose that? Had you gone through Gala sir's lectures, you would have seen that he would have mentioned three main kinds of geometries that are commonly used in these kind of tests. One is a quad geometry, or a coaxial cylindrical geometry. How will that be? You will have a cup. Okay, this cup can be stationary or rotating. In the case of a dynamic shear rheometer, this is stationary. Okay, and we will have a spindle. Okay, a spindle. Okay, so this is the cup and this is the spindle, and this is the moving part. Okay, now the sample is filled in this region. Now when will you use this kind of a geometry? This kind of a geometry you will use for low viscosity materials or Newtonian materials, okay, in such cases you will use this geometry. Now if you take so this is the first geometry which is most popularly used. The second is a cone and plate geometry. How will this geometry look and where will your sample be? You will have a plate at the bottom, okay. It can be of any diameter, it all depends, okay. uh, so you will have a plate at the bottom and you will have a cone like this, a truncated cone. What do I mean by a truncated cone? I have a okay. This is stationary and this is moving. This is the plate and this is the cone. What do I mean by truncated cone? You know the shape of cone, right? It has to be like this. Right? And but because this tip might might like coincide with this plate and cause friction issues, they have truncated this edge like this. Okay. Will that not cause a deviation in your measurements? That will obviously cause. That is why what they've done is they have limited this gap. This gap is so small that this truncated cone is representative of this a full cone geometry. Okay. Here where will your sample be filled? Okay. Here in this case the sample is filled here. And in this case the sample will be filled here. Okay. Now this is for a cone and plate geometry. This is used for again low viscosity samples as well as viscoelastic fluid like samples. Okay. Now the third geometry is a parallel plate geometry. Okay. So how will the geometry look in this case? It will be a flat plate in the bottom which is stationary, and another plate on top which is moving. Okay, so these two. So how will the top view of this geometry look? It will be like this. This is my outer cylinder. This is my spindle and my sample will be filled in this region. here the top view will be like this at any point. So in the bottommost section, if you take, it will be an entire circle, and as an so if you take cross sections at every height, then this inner diameter will keep on increasing. Okay, and the region outside is your sample. Okay, so this is my geometry, this is my sample, and here how will the sample look in the top view? It is a perfect circle, so it is a cylindrical sample. Okay, so here you will have a cylindrical sample. This we will call it as the height of the sample, and this you will call it as the diameter of the sample. With respect to this sample only, I explained you rotational and oscillatory motions of the sample. Okay, where the sample will, the top plate, okay, so this plate is stationary, okay, and this plate is moving, right? So the velocity of the sample which is in contact with the bottom plate is 0, and the velocity of the sample in contact with the top plate is the same as the velocity of the plate. Okay, this only ensures a no slip condition. What do I mean by no slip? Gala sir would have said the sample, if the sample slips, okay, if the sample slips, then my geometry, the speed of or velocity of the geometry, will be greater than that of the sample. Okay, if my sample slips, then my the velocity of the sample is not equal to the velocity of the plate. This is at the boundary. Okay, so now if you see, I told you, so let me show a exaggerated view of this sample. So this is my sample. This has a height h and a diameter d. Now I told you that the velocity in this portion is 0, and this portion is the velocity of the plate. The velocity of the sample is the velocity of the plate, which means there is a gradient in velocity. There is a change in velocity with height, right? If there is a change in velocity with height, okay, this change in velocity is assumed to be linear. It can be anything. We are simply assuming that the change of velocity with respect to the height is linear. Okay. If it is linear, then if my velocity is changing, it means that my strain also varies with height. Okay, but strain rate is constant. Why is it constant? Because I've assumed that the change in velocity is linear. If the velocity gradient is linear. Why am I taking a lot of time, or why am I spending so much time on this parallel plate geometry? It is because all the PG, performance grading test, that you do on your sample is using a parallel plate geometry. Now, so in most of the cases, or the most of the widely used geometries in our case is a parallel plate geometry, where we do the performance grading of bitumen, okay, as per the ASTM standards, okay, and um, a coaxial cylinder geometry, which is used for measuring the mixing and compaction temperature, right? In that case, you will be using that geometry. Just a second. Now, how will you measure? Now, you know the velocity. Just a second. So, when you do, so what are the measurements that you get from a dynamic shear rheometer? The raw measurements that you will get are torque and deflection angle. So, so what is the work of a dynamic shear rheometer? It is to measure the properties of the material, right? Either I can apply a strain to the material and measure stress, or apply stress to the material and measure strain. This is called as a strain controlled test, and this is called as a stress controlled test, because here I am controlling the stress and here I am controlling the strain. Now, actually, I will not be controlling the strain, or I will not be controlling the stress, because stress and strain are computed parameters, right? You have to compute stress from something called as torque, and for strain you have to compute strain from something called as deflection angle, okay. So these are the raw parameters that you will get from the dynamic shear rheometer. Both stress and strain are computed from these raw parameters by using a few constants, okay, which we will call it as a CSS constant, a CSR constant, okay. So there are few constants which are used for this conversion, and these constants will depend on the shape of the geometry. Clear? Now, okay, so when will you use this parallel plate geometry? We will use it for viscoelastic solid like or fluid like materials, okay. When it is a complete solid, you will go for a separate kind of fixture called as SRF fixtures. Here the material is viscoelastic, okay. So in such cases it is better to use a parallel plate geometry. Now if you see, there are different diameters. So the diameter of this parallel plate geometry in asphalt, in bitumen related tests, we use two kinds of geometries. One is a 25 diameter geometry and an 8 diameter geometry. In this case, but there are actually 50 diameters or 100 diameters geometries as well, and in fact there are also 4 diameter geometries. Okay, so predominantly we use these two kinds of geometries. Okay, if you read ASTM D7175, they would have mentioned that you have to go with this geometry for an unaged or RTFO age PG and 8 geometry for a PAV PG. So here I am trying to relate the concepts explained by Gala sir. Okay, he said that if your sample is very stiff, then you have to reduce the surface area of contact with the sample. Okay. Now if you see here, okay, my PAV sample is stiff as, and also it is this testing is done somewhere less than 30 degrees Celsius, or in some cases or 40 degrees Celsius. So in that case you have to go with an 8 geometry because my sample will be very stiff at such temperatures. What will happen if the sample is stiff? If the sample is stiff, it will require more torque, and there are possibilities that the equipment may exceed the torque. The equipment torque limit might exceed. So in that case, if I use a 25 geometry, my torque limit will be exceeded, and also there is something called as a compliance, okay, which we will not talk about in this tutorial. Okay, if you want to know more about it, maybe you can post it in the discussion forum. So because of these few reasons, we go with a diameter, a lesser diameter when the sample is very stiff. At 25 okay, at higher temperatures, these tests are done at higher temperatures, right? Higher temperatures greater than 50, no, not greater than 50, it can be 42 also. Okay, so it is done at higher temperatures. So if you see the high temperature PG, it starts from around 48 or so. So in that case, you will go with a 25 geometry. Why? Because the sample is not that stiff. Okay, so at higher temperatures, what will happen if you go for a geometry with lesser diameter? The lower torque limit may the equipment may reach the lower torque capacity. Okay, which means the torque required is very less, that the data becomes noisy. So it is for these reasons we have these two kinds of geometries. Now this is concerning the diameter of the geometry, right? But the height should also be varied. Okay. In the case of a 25 geometry, you will use a gap of 1 and in the case of an 8 geometry, you will use a gap of 2 Okay. So this is it regarding a parallel plate geometry. So these are the three widely used geometries, and which one do you think has the least contact area with the sample? Which geometry which geometry? Okay, let us go like this. Consider that the diameter is the same. Diameter is same. Let us take the three geometries: parallel plate, cone and plate, and coaxial cylinder. How do you think the surface area? So all these geometries will have some contact surface area with the sample, right? For the same diameter, forget about the heights. Okay, sorry, one second. So here only the top plate, for these two cases only the top plate will be rotating, right? The movable part, let us consider only the movable part. Okay, so here only the top plates are movable, and here only the spindle is movable. Now how do you think the surface area of contact of these geometries, of the movable part of these geometries, will vary? Okay, so if you see, PP will have the least surface area, okay, which is in contact with the movable part, followed by a cone and plate, which in turn is followed by a coaxial cylinder. And as Gala sir would have said, this parallel plate is used for mostly viscoelastic solid like materials. This is used for low viscosity or viscoelastic fluid like materials, and this is used for Newtonian or very or viscosity samples. When will I told you that mostly we use PP and CC for bitumen, okay, except for a few researches, okay, which use a CP geometry. Now how can I use a CC geometry for bitumen when you know that it is a stiff material? You can use a CC geometry on CC geometry for bitumen at high temperatures, okay, where the material viscosity is very less. Okay, so that is how you can make use of all these three geometries for bitumen, because the viscosity of bitumen keeps varying with temperature. Okay, so yeah, so this is the ranking of the surface area in contact with the movable portion of all these three geometries. Okay, now let's go back to the question. A large surface area of interaction, okay, that is what I said about movable portion. Okay, that is where the interaction happens, could be obtained from which among the following geometries? Okay, we saw that this has the least um, contact. Then comes the cone and plate geometry, and then comes the coaxial cylinder. A vane shear test, if you have to know, let us forget about this vane shear. We do not use a vane shear for bitumen. Okay, but if you see a vane shear, it will have a cup, and it will have one geometry with veins. Okay, with veins like this. So in top view, it will have four plates like this, which we will call it as veins. Okay, so if you see the largest surface area of interaction, the answer to this question, as we saw, is a coaxial cylinder. Now moving to the next question, choose the incorrect sentence regarding a cone and plate geometry. Right? So, if you see, the shear rate is constant across the radius. So, in the case of so let us first compare with a parallel plate geometry. Okay, the concept of shear rate, how it is varying with height and varying with radius. So this is my sample, parallel plate sample in the top view, and this is my parallel plate sample in the longitudinal view, or yeah, the elevation kind of view. Okay, so now if you see, I told you that the shear rate is constant with height, right? But this shear rate will be constant in the outermost radius. Okay, because the variation of strain with radius also changes. So let us say I apply a 2% strain, it is getting applied only to this outer edge, which means all the other inner portions, okay, at each radial distance the strain is not 2% but it is something lesser than that. So since the height is constant, okay, the shear rate will keep varying. Why? Because um, in the same time, so what is shear rate? Shear rate is velocity divided by height. The velocity gradient is my shear rate, right? And what is strain? Strain is the deflection divided by height, right? Now what is the relation between strain and strain rate? Strain rate is the rate of change of strain, correct? Now what will happen? At the outermost radius, my the strain is 2%. So the deflection is, let us say it has a deflection of d, okay, and a height of h. H is constant. This is at the outermost radius r. Now let us take, so this is my outermost radius r. Let us take a point here where the radius is say r1. Okay, say it is r1. Okay, what will be the strain there? Strain there will be, just a second. Just a second. Okay, so now at a strain at a radius of r1, okay, it will be some d1 times divided by h, because the deformation at this point is not the same as the deformation at radius r. Okay, it is much lesser than radius r, so the strain is different, okay, but the height is constant, which means at all points along the radius, at each radius, my strain rate will vary because my strain is varying. So this is for a parallel plate geometry. Now what will happen in the case of a cone and plate? Let us take a cone and plate geometry. Okay. If you see here, this is the height, okay, this is the sample, and the height varies with the radius. So if you do the math, the change in the strain with radius is compensated with the change in height. Okay, because at say radius r, okay, it has a deflection of d and a height of h. At radius r1, it has a deflection of d1 and a height of h1. So the strain keeps varying with radius. The strain, the change in the strain, the change in the strain with respect to the radius is compensated by the change in the strain with respect to the height. So in that case, your strain rate will be constant with radius. Okay, I hope this is clear. Okay. So this is correct. The sample thickness is uniform across the radius. This is very obvious. The sample thickness is not uniform across the radius, right? It is something like this. Okay, so it varies with radius. So this is the incorrect option. But let us see other options also. The thickness of the sample is at the center is 47 microns. Okay, so this, I'm not sure if Kala sir has mentioned this, but the sample at the center, okay, this part is very less of the order of microns, and I told you that it has to remain constant. It is 47 microns. So this is also correct. The sample volume required is lesser compared to PP system, obviously, right? Because if the diameter is the same, this much sample is required for a parallel plate system, whereas a portion of this is occupied by cone for a cone and plate system, and the sample required is only this much. This much sample is saved. So in that case, this is also correct. Okay, so the answer to this is the sample thickness is uniform across the radius. So in a dynamic shear rheometer, I told you that there are only two raw measurements. One is torque and one is deflection angle. Okay, so from this torque you can measure stress, and from this deflection angle you can measure both strain and strain rate. So if you see, the shear rate is calculated from, the deflection angle is used to measure strain, and the speed is used to measure the shear rate. So the answer to this is rotational speed. Okay. Moving on to the next question about a dynamic shear rheometer. The hood is used in a dynamic shear rheometer to minimize thermal gradient in the sample, to minimize, okay, and what is this? Yeah, speed to measure shear rate. So this or strain rate. Okay, minimize thermal loss to the environment, keep sample in position, ensure uniform thickness of the sample. So first, let us understand what a hood is. Okay. So if you see, this is the sample sandwiched between. So from now on, most of the reference samples sizes I will be giving with respect to a parallel plate geometry. Okay. So if this is my sample, okay, first let us understand what a thermal gradient is to the sample. If my sample is heated or cooled from all directions, then there will not be any thermal gradient to the sample. So basically, what is thermal gradient? What is gradient? A change in the parameter is gradient, right? And what is thermal gradient? A change in temperature across the height of the sample is thermal gradient. Now, if the sample is heated only from the bottom, then there are chances of thermal gradient to the sample. Okay. So in that case, ASTM, if you see ASTM D7175, they would have mentioned how to eliminate this or how to make measurements, okay, without the artifact of thermal gradient. So what usually you have to do for a thermal gradient to ensure that your sample does not have thermal gradient is you have to allow a considerable amount of waiting time to the sample so that the entire sample attains thermal equilibrium. Okay. And how will you find that each sample will have a different conductivity, right? So some samples might get easily heated up. The entire sample might be in the thermal equilibrium in a matter of few seconds, whereas some samples might take a lot of time to attain thermal equilibrium. In that case, what ASTM D7175 says is you have to first load the sample and use a very small strain measure, okay, say like 0.01% or 0.001%, okay, a very small strain measure, and you have to measure the absolute shear modulus, okay, with time. Okay, and if you see, let us say your sample was initially at 60 degrees Celsius and you want the testing to be at 20 degrees Celsius. So here you loaded the sample or you placed the sample at 60 degrees Celsius in order to bring it to the required shape, okay, because your sample should be workable, right? So you heated the sample and you maybe placed it in the placed it and trimmed the sample. Now your testing temperature is lesser than the 60 degrees Celsius, which is 20 degrees Celsius. So you have to wait a considerable amount of time for the sample to reach 20 degrees Celsius, or you have to wait for some time to reach 20 degrees Celsius, for the entire sample to reach 20 degrees Celsius. Your DSR might indicate that that the temperature is 20 degrees Celsius. You have to be very careful, because it is not the temperature of the sample, it is the temperature of the source, that heat source to the sample. So your DSR is giving 20 degrees Celsius to the sample, but you will never know unless and until you have a kind of a measurement device, okay, a thermocouple, okay, to measure the temperature of the sample. You will never know if your sample has reached 20 degrees Celsius or not. So what ASTM says is, a simple way of doing it is, you measure the modulus, okay, by applying a very small strain value for a time of okay, and plot it against time. So at 60 degrees Celsius you expect the sample to have a lesser modulus, right? And at 20 degrees Celsius, obviously the modulus of bitumen will increase. So it will from time t, the modulus will keep on increasing, okay, because with time the entire sample is attaining thermal equilibrium. Until that, at least some portion of it was having a temperature of 60 degrees Celsius, maybe the top portion, because here I am saying that only the lower portion gives you the heat, so is controls the temperature, okay, is providing temperature to the sample. Now it will increase, and at one point of time it will reach a constant value, and this time you should allow for the sample to reach thermal equilibrium. Okay, this is how you will find out how each sample how much time should be given for each sample to find out for it to reach thermal equilibrium. Okay, So this can be, so this has nothing to do with the hood. Okay, so it is, even if you have a hood, okay, the entire sample has to reach thermal equilibrium, right? So in that case, your hood, though it helps in attaining maybe the thermal equilibrium faster because it has a controlled environment, it does not minimize the thermal gradient because this can be eliminated by giving a waiting period for the sample to reach thermal equilibrium. Okay, so what does the hood do? So when I say hood, it is, say, an enclosure, okay, that covers this sample area, okay, and prevents heat loss or thermal, yeah, in common, okay, in general you can say thermal losses to the environment. Your environment, say, mostly you will be operating the rheometer in a air conditioned environment, okay, and let us say you're testing it at 60 degrees Celsius. Obviously there will be a thermal, a, an exchange of temperature with respect with the surroundings, okay. So in that case, so that should not happen, right? So you should have a controlled environment. So for that you use a hood, okay, you use something called as the hood. So the answer to this is minimizing thermal loss to the environment. So it has nothing to do with keeping the sample in position, or it has nothing to do with ensuring whether the sample is of uniform thickness or not. So the answer to this is minimize thermal loss to the environment. So moving to the next question. Okay, yeah, we will first see questions related to DSR. Yeah. So this one. And in an oscillatory shear test, the following are the raw parameters measured by the rheometer. So time and again, all through this lecture till now, I've been telling you that torque and deflection angle are the raw parameters measured by the rheometer. Okay. Stress and strain are computed from these two raw parameters. So let us again come from first and solve questions related to viscosity grading or performance grading. So it can be either of these two. Now before we get into viscosity grading, I would like to say something about the evolution of the grading system of bitumen. Okay, so let us see that first, but before that, first please give me a few minutes. Okay, so let us talk about the evolution of grading system of bitumen. So let us talk a very interesting story now, okay, about this evolution. So initially, before this penetration grading, okay, before this penetration grading, how they used to identify the consistency of bitumen is by chewing bitumen. Okay, so even sir's earlier lectures, sir would have said that they chew the bitumen to find out whether it is sweet or sour, and find out if it has a, and find out how much sulfur it has. Okay, so before that, so before this penetration grading, what they used to do is they used to chew the bitumen to find out the consistency of bitumen. And in that case, what do you think the temperature of testing would be? It would be the body temperature, the normal body temperature. Okay, but this is highly subjective, right? So it varies from person to person, and it is not a standard measure. Like chewing um, is a very naive way of identifying the consistency of bitumen. So what happened after that is they introduced an equipment called as penetrometer. Okay, to have some uh, standard way of measuring the penetration of to have some standard way of measuring the consistency of bitumen. And that is when the penetrometer came. Okay, and here initially they were doing the testing at 4 degrees Celsius, and later they uh, it was shifted to 25 degrees Celsius. Now what this penetrometer actually does it, so there will be a sample. Okay, there will be a needle. Okay, and this needle will be allowed to drop. So here initially you will place the needle at the surface of the sample, and you will release the needle of weight 100 grams and measure the penetration at the end of 5 seconds. Okay, you will do it at 3 points, and you will take the average value. So this is the penetration value of bitumen, which is recorded in 1/10 of millimeter. So if I say my penetration value is 45, it means that my penetration value is 4.5 mm. So so what initially they did is they graded bitumen based on this penetration value. So had you seen earlier, they called it as the penetration grading, and the bitumen values, okay, the grade will be like 30 bar 40 or 60 bar 70, like that, 60 bar 80, like that. It means that the penetration value of that bitumen lies between 30 and 40 mm, 40, okay, or 3 to 4 mm. Likewise, 60 bar 70 means the penetration value lies between 60 and 70. Now, how can you judge bitumen? If the penetration value is less, then my bitumen is stiff, and if it is high, my bitumen is soft. Kind like, okay. So this is what they did for penetration grading. But this test was done only at 25 degrees Celsius, right? And you know that my bitumen is subjected to different temperatures, right? So this is done only at 25 degrees Celsius. So if I have to find out something, the behavior of bitumen at 60 degrees Celsius, okay, where it is prone to rutting, then it is difficult, right? Because you cannot do penetration gradient for grading for bitumen at 60 degrees Celsius. So in that case, they moved on to something called as viscosity grading. So what will this viscosity grading do? The basic the grade is given based on viscosity, but it also ensures that other consistency measures are also met. So what do I mean by this? Say if you see this temperature, this penetration grading does not take into account the temperature susceptibility of bitumen. So what is this temperature susceptibility of bitumen? Let me make a plot of temperature and say penetration or viscosity. It can be anything. Okay. So if let us say I'm measuring penetration, let us take only penetration. this penetration at 25 degrees is what I'm measuring for a penetration grading. Okay. Now let us say the penetration at 25 degrees is this value for a bitumen A. Okay, and I'm measuring penetration at, I cannot measure penetration at 60 degrees Celsius. Okay, but still, okay, let us say I'm measuring the viscosity and it is, or viscosity, I'm measuring viscosity at 60 degrees Celsius and it gives me a viscosity, a lesser viscosity. Okay, so this is my bitumen A. Now let me take a bitumen B which has the same penetration at 25 degrees Celsius, but the viscosity at 60 degrees Celsius is somewhat here. Okay, so this is bitumen A and this is bitumen B. So if you see, now if I want to choose a bitumen, okay, based on just penetration grading at 25 degrees Celsius, I cannot be sure how it is going to behave at 60 degrees Celsius where it is more prone to rutting, right? So in that case, I need some kind of a grading system which can track this temperature susceptibility of bitumen. As Sir said, a bitumen with a lesser gradient is better, right? So how will I track this gradient with the, instead of measuring the temperature at each these measures, consistency measures at each and every temperature, what they did, it is just grading, right? So you cannot be meticulously doing it at every temperature. No one will be doing that. So in that case, what they did is they identified a few temperatures, say penetration at 25 degrees Celsius, viscosity at 60 degrees Celsius, and one more viscosity at 135 degrees Celsius to represent the temperature close to the mixing and compaction temperature of bitumen. So what they did, they measured the consistency measures at these three temperatures, okay, and they kind of set a limit for it. So when they set a limit for it, what they actually did is they tried to monitor this slope of the temperature susceptibility curve. Okay, so if the slope is less, then it is a good quality bitumen, right? So that is when they moved on to viscosity grading. Now if you see this viscosity grading, it will have penetration at 25 degrees Celsius, viscosity at 60 degrees Celsius, and viscosity at 135 degrees Celsius. It also has softening point, okay, and so on and so forth. And out of this, only this has a range. Okay, all these will be mentioned as either it will have a minimum limit or a maximum limit. Okay, and if you see, you have to check whether your bitumen satisfies all these parameters to be graded as VG10, VG20, VG30 or VG40 bitumen. Okay, and out of this, if my bitumen has VG10, then it has a viscosity of 1000 poise. If my bitumen is of VG40 grade, then it has a viscosity of 4000 poise. So there we saw that if my penetration value is higher, then the bitumen is softer. But here, if the viscosity grade is lesser, which it means that the viscosity is less and the bitumen is softer. Okay. Now, why did they move from viscosity grading to performance grading? So viscosity grading, as you saw, it is measured at a few temperatures of 25, 60 and 135 degrees Celsius. But is your pavement going to be subjected to exactly 25, 60 or 135? Or, sorry, not 135, 25 or 60? No, right? It is going to be subjected over a range of temperatures. So in that case, what they actually did is, instead of identifying a few temperatures and measuring the consistency, measuring or finding the behavior of bitumen at those temperatures, because I'm measuring the behavior of bitumen at 60 degrees Celsius, okay, but my pavement temperature may be 70 degrees Celsius, right? We don't know. And if you see here, all these are empirical measures. None of them have uh, a theoretical base to it. Like, you do not apply a load externally to bitumen, okay? So there's no influence of loading rate in each of these testings, though my bitumen will have an influence on loading rate, right? So they do not have any theoretical background to it. They are all empirical measures. So what they did in performance grading is, now there are two things. In the performance grading, you will have the influence of loading rate, okay? And one more thing is, the most important thing is, my bitumen, the temperature of the place may be 70 degrees Celsius, but I'm identifying bitumen based on tests conducted at 25 degrees Celsius or 60 degrees Celsius. It is going to be subjected to over range of temperatures, right? So my temperature of the place may be anywhere between, say, 20 degrees Celsius to 60 degrees Celsius. Let us say my highest temperature is 70 degrees Celsius, okay, sorry, 70 degrees Celsius, and the lowest temperature is, say, 20 degrees Celsius. And at any point, point in time, okay, it can be subjected to anywhere between 20 and 70 degrees Celsius, because these are the extreme values of temperature to which the bitumen is subjected to. So in that case, what they try to do is, they took a bitumen, okay, and they subjected it to a few testings at high temperatures. So what do you expect the bitumen to have at high temperatures? It should be stiff, right? So in that case, they identified a parameter called as G star by sine delta, okay, and it should have a minimum stiffness of 1 kPa or 2.2 kPa in the case of unaged and short-term aged bitumen respectively. So why is that? Because at high temperatures, it should have a minimum stiffness, only then it will not rut, okay. Then they subjected, let us say I'm given 3 bitumen A, B and C, okay, and I have to check if my bitumen will survive in this temperature of 70 degrees Celsius, okay. What I will do is, I will subject this all these 3 bitumen to a testing at 70 degrees Celsius and find out if the minimum value of if it has a minimum stiffness, okay. But so that is how you can identify whether your bitumen is suitable to that place or not, right? If your bitumen is suitable to that place or not. Let us say at 70 degrees Celsius, my bitumen A has a G star by sine delta of 0.9. This has, say, all of this is done at unaged conditions, okay. Let this have 1.5 and this have 2.5, okay. It means, so obviously bitumen A cannot be used, because at 70 degrees Celsius, it has to have a minimum stiffness of 1 kPa and it has only 0.9 kPa. So obviously bitumen A will fail. It will undergo rutting, okay. If you see bitumen B and C, they will survive this climatic condition. So that is what this performance grading actually means. What it actually does is, either you can either you go from the temperature of the place and identify the bitumen, or identify the grade of bitumen and see where, in what places it can be used. So if you identify the temperature of the place, to be 70 degrees Celsius. Okay, then you come back and find out a bitumen which can survive at 70 degrees Celsius. Okay, or you do testing in bitumen. Say I test bitumen A, B and C. Okay, and I find out what is the grade of bitumen based on this performance grading, and then you can use this bitumen. You can say that where this bitumen can be used. Okay, so here the grading is based on climate, right? I'm using the temperature to grade the bitumen. So here penetration grading, you did it based on penetration. Viscosity grading, you did it based on viscosity along with other parameters as well, whereas penetration grading, you're doing it based on climate. Okay, so this is all about the three types of grading till now. So if you see, as per Indian standards, for unmodified bitumen we stick to only viscosity grading, whereas for modified bitumen we have included performance grading in the latest standard. Okay. Okay. And now a typical bituminous binder exhibits. So if you see, what actually do you expect the bitumen to have? It should have at low temperatures 60 degrees Celsius. At low temperatures it should be soft, and at high temperatures it should be stiff. But what will actually happen is, at low temperatures it will be, if a bitumen is stiff, then at high temperatures it will be it will be even more stiffer. So I should say it the other way around. Okay, so let us say at high temperatures my bitumen is stiff, which is what I want. But what will happen in reality, at low temperatures it will be even more stiffer. Or okay, so if this condition is satisfied, it will fail in this case. Okay, at 25 degrees Celsius. Now if my bitumen is soft at 25 degrees Celsius, then at 60 degrees Celsius it will be even more softer. So if it satisfies this criteria, this will be failed. Okay, so this is what a real life bitumen or a bitumen actually exhibits. Okay, so let us go through one by one. What does low penetration means? Low penetration means a stiff bitumen. Okay. And low viscosity, is a soft bitumen. So is this what your bitumen will exhibit? Obviously no, because if it is stiff, it will exhibit an even stiffer property, or it will have a higher viscosity. So low penetration and low softening point. So low softening point also indicates that your bitumen is soft, because even at low temperatures it has started to melt. So this also exhibits this case. So low penetration and high viscosity is stiff and stiffer. So this is what your bitumen will exhibit. So in that case, this is the answer. High penetration and high viscosity, this is what actually you want from bitumen. So high penetration is soft and high viscosity is stiff. So this is what you want, but this is what it will exhibit. Okay, so the answer to this is low penetration and high viscosity. Performance grade for bitumen is based on penetration at 25 degrees Celsius. No, this is penetration grade. uh, based on viscosity at 60 degrees Celsius? No, this is viscosity grade. Based on climate? Obviously yes, we just saw it now. Is it based on kinematic viscosity at 135 degrees Celsius? No. Okay, so the answer to this is based on climate. Okay, so here bituminous binder plays a critical role in what? We saw that it has criteria for rutting and fatigue. Okay, so in order to prevent rutting, it has to be um, stiff, and in order to prevent fatigue, it has to be soft, right? It similarly, in order to prevent low temperature cracking, it has to be soft. Okay, and in order to prevent bleeding, also it has a criteria. So it plays a critical role in all these uh, all these distress criteria. Okay, though these three are the main types of distress, this is also a distress which for which bituminous binder plays a critical role. Okay. Okay, then moving on to the next question: which bitumen will you choose for your bituminous pavement construction? A bitumen having low penetration at 25 degrees Celsius and low viscosity. So low penetration means, so what do I want from bitumen? It should be 25 degrees Celsius, 60 degrees Celsius. It should be soft and stiff. So what does my A say? It has low penetration. Low penetration is stiff, and low viscosity. Low viscosity is soft. So obviously no. A bitumen having low penetration and low softening point. Low penetration is stiff, and again this is soft. A bitumen having low penetration is stiff, and high viscosity is again stiff. This is also not the case. Having high penetration is soft and high viscosity is stiff. So this is what I want from bitumen. Okay. So bitumen having high penetration and high viscosity. Moving to the next question: which of these distresses will be predominating when the pavement temperature is near 0 degrees Celsius? So rutting, obviously it will occur at high temperatures, so no. Low temperature cracking, obviously yes. Okay, when the temperature is very low, it is prone to low temperature cracking, and there are two types. One is where the so there are two types of low temperature cracking. Okay, so one is where the temperature is so low, say below the glass transition temperature, where without even any load the bitumen shatters like glass. Okay, and the other is a temperature greater than this critical temperature. Okay, but due to repeated loading, a combination of this low temperature and repeated loading will cause low temperature cracking. So there are two types of low temperature cracking, and one of that is so that is why a pavement near 0 degrees Celsius will undergo low temperature cracking. Bleeding, do you think bleeding will occur at 0 degrees Celsius? No, bleeding will occur only when the bitumen is able to flow, right? So so this is what constitutes bleeding. And skid resistance, obviously it will have skid resistance, but skid resistance will occur when the pavement again when the bitumen has flowed out. When there's bleeding, then all the bitumen is on top and there's no skid resistance, right? The vehicle is prone to skidding. So this is also not the answer. The phenomenon of densification and shear flow on the pavement wheel path at high temperatures is what? So, if you see, when you construct the bituminous pavement, right, you will compact the bituminous pavement to an air void content of 6 to 8%. Okay. Now that is a primary compaction. Now, due to the repeated application of vehicular loading, traffic loading, your bitumen will the air voids in the bitumen will keep on reducing, and that process is called as densification. Okay, and this we will call it as secondary compaction. But if your bitumen is not so, this is expected in a pavement. Okay, but if your mix is not properly designed, this densification along with this, so this is densification and this is shear flow, along with this shear flow only will come out as rutting. So at high temperatures, obviously you know it is not low temperature cracking, bleeding, it is just oozing out of bitumen from to the surface. And skid resistance, it is the resistance to skidding, right? So that also has nothing to do with this densification of shear flow. So the answer to this is rutting. Moving to the next question. The temperature of the pavement is expected to be higher at depth of dash below the surface of the mixture. So, if you see, we need to measure the high temperature and low temperature of the place in order to find out the high and low pavement temperature in order to find out what grade of bitumen can be used for this pavement, right? If you see, the high temperature is measured at a depth of 20 mm from the surface, because what they did is they made a plot of temperature versus depth, and they were able to see that compared to the top surface, the temperature was maximum at a depth of 20 degrees Celsius, and then it kind of decreased. Okay, so they use this. So you have to always take the critical value, right? So it was found to be maximum at a depth of 20 mm from the top, and so whenever they wanted to measure the high temperature of the place, they measured it at a depth of 20 mm. High pavement temperature, they measured it at a depth of 20 mm from the surface. Whereas low temperature, it was found to be minimum at the surface, so low temperature they measured at the surface. Okay, so the temperature of the pavement is expected to be higher at a depth of 20 mm below the surface of the mixture. Okay, so the next question, a bitumen is said to have good temperature susceptibility if what? So you know, we made a plot of consistency versus temperature, and we said that a bitumen with gradual changes in the consistency measured with temperature is said to have a good temperature susceptibility. So the variation of consistency parameter over a temperature range is gradual. Yes, the variation of temperature consistency parameter over a temperature range is drastic. What does this mean? It means that if it is a stiff bitumen, okay, if my criteria is satisfied at 60 degrees Celsius, say that my bitumen is stiff, then it will be even more stiffer at 25 degrees Celsius, which is not what I want. Okay, so in that case, this is not ideal. The consistency parameter shows no variation across a temperature range. Will it show no variation across a temp? Obviously, if it has no variation, it is a maybe it is a good temperature susceptible bitumen, but obviously the bitumen changes with changes in temperature, right? The properties of bitumen changes with changes in temperature. So you cannot expect this from bitumen, but you can only expect the bitumen to have a gradual change in slope. Okay, the temperature, the consistency curve. Okay, so this is the answer. Glass transition temperature is above 0 degrees Celsius. No. Okay, so the answer to this is A. As per ASTM D 2872, rolling thin film oven test, okay, was carried out at a temperature of what? So this we saw it last week as well as sir explained it this week, like as to what temperature should be used and at for what duration. Okay, and the temperature has to be, so RTF, a rolling thin film is a short term aging which is used to mm, simulate the um, aging that happens due to the uh, mixing and compaction in bitumen, right? Mixing or the storage temperature in bitumen, right? So that has to happen. So for that, the temperature has to be close to the mixing and compaction temperature, which is 163 degrees Celsius. Okay, so here there are two options with 163 degrees Celsius, and how many minutes is it actually done? It is done for 85 minutes and not 70 minutes. Okay, so the answer to this is 85, B. Okay, which of the below equipment is used to measure the viscosity of the binder at 60 degrees Celsius? So uh, if you see here, at 60 degrees Celsius, you can measure viscosity using a dynamic shear rheometer also, okay, and a rotational viscometer, but there are a few limitations. One is the torque limit of the equipment. So here it will have a torque limit at 60 degrees Celsius. The viscosity will be very high, so you cannot uh, measure viscosity at 60 degrees Celsius. You can okay, so and a dynamic shear rheometer also, viscosity can be measured, but the question is which equipment is already being used to measure the viscosity of binder at 60 degrees Celsius. So if you see the code, it is done using a capillary viscometer, right? So the answer to this is capillary viscometer. Others may or may not, other equipments may or may not be used, but the question is what is actually or currently in practice. It is a capillary viscometer, right? A vacuum capillary viscometer. To quantify the resistance to rutting in the field, the binder is tested using a DSR. Okay, resistance to rutting. Okay, which so this testing is done at unaged conditions and short-term aged conditions, right? For this it was 1 kPa. The criteria was G star by sin delta should be a minimum of 1 kPa, and here G star by sin delta should be a minimum of 2.2 kPa. Okay, and in both the cases you are checking the minimum stiffness required. Okay, so the answer to this is all the above. So it is tested using a dynamic shear rheometer in the laboratory at unaged conditions, in the laboratory at short-term aged conditions, and also to check the minimum stiffness requirement. So the answer to this is all the above. Okay. Short-term aging of the binder simulates the stiffening of the binder during what? So obviously it is not during service. For that you will do long-term aging or long-term aging using a pressure aging vessel, right? Mixing and compaction, not only mixing and compaction, so it includes storing, mixing and hauling. Okay, so it is for storing, mixing and hauling, and not storage or service or mixing and compaction. So the answer to this is storage, mixing and hauling. Okay. The binder specifications presented in table 2 of ASTM D3381. So this is what is used in US, right? And I believe it is US if I'm not wrong. Okay, so please correct me if I'm wrong. Okay, so here this is the only code to give two tables, table 1 and table 2. And if you see, both these tables had the same viscosity requirements, but the penetration of table 1 is less than penetration of table 2. Okay, So what do you want a good bitumen to have? It should have high penetration at low temperatures, right? So this is what table 2 has, high penetration. For the same viscosity, it has high penetration at low temperatures. So if you see, if if it has high penetration and so let us convert this penetration or viscosity. So if it has high penetration, it means it has low viscosity, and say the viscosity is constant. So for table 1 and 2, viscosity at 60 degrees Celsius is constant, okay, and the penetration for table 1 is lesser than the penetration at table in table 2, okay. So which means viscosity in table 1 is more compared to viscosity in table 2, right? So this is table 1 and this is table 2. So which do you think has better uh, temperature susceptibility? Table 2 has better temperature susceptibility compared to table 1 of the same code, okay. So that's it for this week, right? So if you have any questions, please feel free to post in the discussion forum, okay. Thank you.